Okay, I want to talk about something called similar matrices. Okay, before I do that, I want to chat a little bit about what we've been doing with eigenvalues and eigenvectors here. In our previous formulation from the last video, we used the determinant of A minus lambda I, and we set that to 0 to find the eigenvalues of the matrix A, the square matrix A. Um, your book uses a slightly different notation, okay? This is ultimately equivalent here. But they take the determinant of xi. Remember, I is what? The n by n multiplicative identity if A is an n by n matrix, okay? X is just a scalar here. It's playing the role of what we called lambda before. Now what I've got here that I'm marking right here, the original, that is the more standard formulation. This formulation is equivalent, okay? They've changed the order in which they're taking the difference of the matrices here, and they've changed lambda to x to make it look like a polynomial in x, okay? You can see that's not going to change things much here. You're going to get exactly the same eigenvalues that you did before. What I had up here is a little more standard with the lambda, but we'll go ahead and stick to what your book is doing here. But it was good to introduce it actually with a more standard formulation that you'll probably see elsewhere. Okay. By the way, we write this way: the determinant of xi minus a. Remember, if a is an n by n matrix, then what you end up with is what? A polynomial of degree n. In this case, that polynomial would be in x, in the unknown or variable x. Okay, we designate that polynomial by c subscript a of x. Okay, so it's written this way, and we call that the characteristic polynomial, and I mentioned that in the previous video. So the c stands for characteristic, and so this is a polynomial in x the way they're doing it, and that's the way we'll do it for most of the time, at least from now on. Okay, so that's the characteristic polynomial of the matrix A. Okay, and so in the book they're setting that characteristic polynomial to 0 instead of this thing to 0 up here. But at worst, you're what? Just changing the name of the variable, or multiplying at worst that polynomial by -1. Okay, so we still get the same eigenvalues. Okay, now I wanted to talk just a little bit about what happens with eigenvalues, or eigenvectors I should say, of repeated eigenvalues. Of course, you know that what? From your college algebra experience, that if I give you a polynomial and have you set it to 0, that there might be some repeated zeros, right? Okay, there might be some repeated roots of that equation set to 0. Okay, so we might have repeated eigenvalues. What happens when you have repeated eigenvalues? Well, what I want to show you is different things can happen. Okay, okay. Something I want you to prove, this is just an exercise for you. We will actually mention how it's proved as we go throughout, but if you want to stop and think about it just for a second here, it's pretty easy. If a square matrix is upper or lower triangular, then its eigenvalues are its main diagonal entries. Should be an L over there. Main diagonal entries, okay? Alrighty. So, that should be easy to prove, okay? We will see why it's true here as we go through, but you should think about it and see if you can prove that statement, okay? Does that seem clear? Okay, well, if that statement is true, if I have the following matrix, 3 by 3 matrix, A is 1, 1, 1, 0, 1, 2, 0, 0, 1, then what would the eigenvalues be? The eigenvalues would be, because this is an upper triangular matrix, the eigenvalues would be the main diagonal entries, which are what? Ones, right? 1, 1, 1. Okay? Obviously, repeated eigenvalues here. Okay? Let's just go ahead and see that. Okay? Here is the characteristic polynomial, right? That's our designation for it. C subscript cap A of x. Okay, we said that's the determinant of what? X times the what? N by n identity, in this case 3 by 3 identity, multiplicative identity, minus your matrix A. Okay, what would that amount to here? So I'm using the vertical bar notation for determinants. That would be what? X minus 1, negative 1, negative 1, because I'm subtracting A here, you see. 0, x minus 1, negative 2. Okay, 0, 0, x minus 1. Now, let's take the determinant of that. Well, here's you go. Here's the reason why this holds. You remember from our study of determinants that what? The determinant of a what? Upper triangular or lower triangular matrix is going to be what? Square matrix, obviously, is the product of the main diagonal entries. Okay? Now, if you look here, since that's true, okay, so we're not going to go through the entire expansion here. We're going to use that little fact then. All I'm getting for my determinant here is the product of these main diagonal entries. So that would be x minus 1 times x minus 1 times x minus 1, or x minus 1 cubed. And you could see when we set that to 0 that we're just going to get what? Those main diagonal entries, 1, 1, 1. And we say what? 1 is a 0 of multiplicity 3. Right? Okay? 1 is a 0 of the characteristic polynomial with multiplicity 3. Remember that language from college algebra. Okay, but let's just take this case here. We've got x is equal to 1. That's the only eigenvalue, although it's repeated. Okay? And you remember to find the eigenvectors, which in this case I'm calling v. I had that x before, so I covered it up here. I've already got x over here. So I'm going to call the eigenvector v instead. Anyway, so we should have this. xi minus a times the eigenvector v should give you what? 0. Okay? That's just originally saying, you remember, a times v is equal to, I was calling it lambda last time, like most people do, but your book would call it x then. X times v. This is what? Just rewriting this, subtracting this guy on both sides, and then factoring out the v. Okay, that's all you're doing. Alrighty? But let's set that up then. Okay? Now, xi minus a times v is the 0 vector. Okay, so writing it as an augmented system here with x is actually equal to 1. Okay, so I've come up here. I've let x equal 1 here. But I'm not writing it as a determinant anymore. I'm writing it as an augmented system. We would have this. Okay? Does that make sense? Is that clear? Alrighty. Now let's do the arithmetic. So I've subtracted from the eigenvalue. So we get the following: 0, negative 1, negative 1, 0, 0, 0, negative 2, 0, and then a row of zeros, which tells us nothing. Okay, except 0 is 0. Okay, now I'm calling my, I will be doing this, I'm calling my eigenvector v with entries v1, v2, v3. Okay, so this is the v1 column, this is the v2 column, this is the v3 column. There it is in row reduced echelon form here. And you can see what this would imply. This would say that what? The first equation would be what? v2 equals 0. The second equation is what? v3 equals 0. So that means v2 and v3 are equal to 0. The last equation says 0 equals 0. That doesn't do anything for us. Notice that there's one undetermined value, which is what? The v1. Okay? Alrighty? Remember, there better not be a unique solution to this. Otherwise, what? You didn't find an eigenvalue. Remember, eigenvectors cannot be the 0 vector. Okay? I'll mention that again right here. So anyways, the only solution to this, there's infinitely many solutions to the system, but all the solutions would look like this, right? From Gaussian elimination. V1, 0, 0. Okay? V1, 0, 0. So that means V1 is free, but V2 and V3 are both 0. So we've got that. And then I just factored out the V1. So we would say that what? 1, 0, 0 is an eigenvector. Okay, any non-zero scalar multiple of that would also be an eigenvector. Okay, with what? Corresponding eigenvalue 1. Now you could actually test that with the original here. Multiply by 1, 0, 0, and you get 1, 0, 0 times 1. Okay, it works here. Alrighty? So here I'm saying v1 better not be 0, though. Otherwise, you would get 0 for your eigenvector. And you can't have that, right? Eigenvectors are non-zero vectors. Okay? Well, anyways, let's go to this second example. Okay? So I want you to see there's essentially what? If, except for 0, this would, I mean, this is almost like the span of the vector, what? 1, 0, 0. Only you're kicking out the 0 vector, okay? So this is like one-dimensional, except, of course, it's not really what a subspace of anything at this point, because what 0 would be is not included here. Okay, if we did throw in 0, which is not an eigenvector, and call that an eigenspace, which is what we will do later on, some people do. Now, we're not saying 0 is an eigenvector. We're just saying if you threw in 0 together with all the eigenvectors, you would have a space we could call the eigenspace. And that would be one-dimensional. Okay? But let's not worry about that language right now. Let's go on. Let's take the second example. I've got a slightly different matrix here. Okay, slightly different from the first. Okay, so I've got 1, 0, 2, 0, 1, 1, 0, 0, 1. Okay, that's my new way. Once again, this is an upper triangular matrix. The eigenvalues are going to be 1, 1, 1 again. Okay? Now, let's go ahead and set this up one more time here. Okay, so I've got 1 minus 1, 0, negative 2, 0, 1 minus 1, which is 0, negative 1, 0, 0, 1 minus 1, which is 0, and then 0. Okay, so this is my new system here. Okay, now if you take a look at this thing, we don't even need to put this in row-reduced echelon form. You can see clearly that V3's got to be 0, but what? V1 and V2 are undetermined, right? They're free. Okay, so this equation up here would only be saying what? I just threw this in here for the sake of completeness. 0 V1 plus 0 V2 equals 0. Now we know from this equation that V3's got to be 0. And I'm just pointing out that what? V1 and V2 are completely free, aren't they? Okay. All right. So we've only got one pivot variable is the point. We've got two free variables. Okay, now, so if I was to write my general eigenvector V bar, which is V1, V2, V3, I could say what? Well, it's V1, which is free, times 1, 0, 0, and then what? Plus V2, which is 0, 1, 0. So again, you notice that this is almost the span of what? Two eigenvectors, okay? Notice that we can't have both V1 and V2 to be 0, which is written succinctly this way, right? That's equivalent to saying it is not true that both V1 and V2 are 0, okay? Or in other words, it's saying V1 and V2, at least one of those is non-zero, okay? Because otherwise we would have 0 as an eigenvector, and we don't like that, right? Okay, but you see what's happened here? This is you've got eigenvectors here. Yeah, there's infinitely many of them. But here you've got eigenvectors also. But this is, if you threw in the 0 vector in this as a space to get a subspace, this would be the span of these two vectors. It would be two-dimensional. That's what we would call an eigenspace. But again, an eigenspace is also throwing in 0, which is not an eigenvector. Okay, I'm getting tired of saying that. But anyways, there it is. And you're probably tired of hearing it. Anyways, there it is, one last one. Suppose that A is just the identity here, the 3 by 3 multiplicative identity, so 1's down the main diagonals. Okay, so I'm not going to go through this in complete detail. You should probably see what's happening for these previous ones. You can see that once again the eigen values are 1, 1, 1. Okay, And if you actually, go 1 minus, go 1I minus A, set that to 0, you're going to actually have 3 solutions here, basic solutions. 1, 0, 0, 0, 1, 0, and 0, 0, 1. So you see, with repeated eigenvalues, I can have different situations approaching here, okay, or occurring. I guess I should have boxed this in. Box in your final answer, okay? All right, so different situations can occur when you have repeated eigenvalues. What happens if the eigenvalues are all distinct, though, meaning different? Well, we'll talk about that later. Let's talk about something else right now. Similar matrices. Let's go to a definition here. Now, here's the definition. Suppose that A and B are n by n matrices, okay? So they're square matrices of the same dimension, okay? Okay, just keep that in mind. You could actually derive the truth that they are square matrices of the same dimensions from the definition, but I'm going to go ahead and throw that in anyways. Now, here's my definition. A is similar to B if A equals P inverse B times P for some invertible matrix P. Obviously, invertible matrix, because we had P inverse written right here. Okay? So P better be invertible, otherwise this would have no meaning right up here, right? Okay? Now, I'm going to write it this way, and you read that. A is similar to B. Now, I'm not sure your book does that. I don't think it does. A lot of people probably don't, but I'm going to do it. That's a little symbol actually comes from geometry, that similarity symbol. That's written as similar, okay? So A is similar to B if you can find an invertible matrix P such that A is P inverse B P. Now this is might look kind of kooky right now, but this is going to make more sense as we use it more and more. Okay, not just in this video, but in the next. Okay, let's just go with the definition for now. Okay, let me throw something in here. Okay, this is sometimes called a reflexive property. Okay, A is similar to itself. Okay, A is similar to itself. How would we know that? Well, notice that A is what? I inverse times A times I, where I is, of course, what? The n by n multiplicative identity. Okay? I inverse is going to be the same as I. You can see, and A times I is going to be what? In either order, it's going to be A. So this is clearly true. Well, we found a P. The P happens to be what? I. So that A must be similar to itself. Well, that's nice. Here's another property. We're going to call this the symmetric property, as a matter of fact. But I'm saying if A is similar to B, then B is similar to A. Okay? So here we could say it A and B are similar. Okay? A and B are similar. So there's not a direction as far as similarity goes, like my original definition sounds like, right? Okay? All right, let's see why that's true. Let's say A is similar to B. That would mean that what? There exists a P such that what? A is P inverse B times P, right? All right, some such P exists. So that, suppose I did the following little calculation. Suppose I went P times A times P inverse. Okay, just a little calculation I'm going to do. Then that would be what? P times P inverse B P times P inverse. Okay? Clearly, all I did was what? Substitute for A, this formulation. Okay? Now we have all kinds of wonderful properties with matrix multiplication, such as what? The associative property. So what I can do is what? I'll combine the P and the P inverse in front here, so I will block those off with parentheses, and I'll put the P and the P inverse at the end together too with parentheses, okay? And then I've got B sitting there in the middle. But wait a minute. What is P times P inverse in either order? Why, it's I. So we have P A, P inverse is I, B, I, but we know that's going to be what? B, because I is the multiplicative identity. Okay? So now I have B being equal to what? P, A, P inverse. Now, I want you to notice that P inverse is really P, right? The inverse of P inverse is P. So instead of P here, I'm going to think that is what? P inverse. So that's P inverse times A, P inverse. Okay? So I've got what? A here, the inverse of some matrix sitting here, and then what? That matrix sitting here. Okay? So what does that mean? Well, that means that B is similar to A. Aha! And that's a symmetric property. So now we can say A and B are similar. B and A are similar. It means ultimately the same thing, although what? You would have to have different P's involved, depending on which way you're writing it. Okay? Alrighty? This last property. A is similar to B and B is similar to C. Then what do you think is true? A is similar to C. Okay? What this means is ultimately similarity is something we call an equivalence relation among the square matrices of a particular dimension. But let's go ahead and see if we can prove this. A is similar to B. Okay? What does that imply, or equivalent to, I could say, if and only if, actually. A equals P inverse B, P for some P. Okay? How about B is similar to C? What does that mean? That means B is Q inverse times C times Q for some Q. Okay? Now notice here, because I'm talking about different matrices in each case here, I couldn't use P here in this formulation. I had to give a different name for that matrix. I'm not saying it's the same matrix as P up here, right? These may be, B and C are completely different matrices. Well, I'm saying A and B, those are two matrices. B and C, those are two matrices. You're probably not going to have the same P here in both cases, right? All right, even though they're similar. So I have to give her a different name on this one, okay? So for some Q. All right, let's keep going. Now, A is P inverse times B times P, which is P inverse times what? Q inverse C, Q, and then I've got my P again. Again, I just substituted for B here. I just put in that formulation for B. That's all I did. Okay? And then we're going to go ahead and use the magic of the associative property. So I've got C sitting right here in the middle. And what? I've used parentheses to combine these two. P inverse Q inverse, and then C times QP. Okay? But do you remember P inverse Q inverse is actually what? The inverse of Q times P. Yes, don't forget the order gets reversed in the product when you're taking what? The inverse. Same holds true if you were taking a transpose, by the way. Remember, the order gets reversed here. That's easy to prove. If you don't remember, go back and prove that to yourself. It's easy. Okay? These two are equal. Oh, but what would that be saying? That would say A is similar to C because I've got some matrix, obviously invertible. Okay? So that matrix inverse times C times that matrix gives me A. Therefore, A is similar to C. This is sometimes called the transitive property. Okay? Alrighty, so there you go. Similarity is an equivalence relation among the square matrices of a given dimension and partitions those matrices into equivalence classes. Okay, so it divvies up the square matrices of a particular dimension, okay, into what we would call equivalence classes of symmetric matrices. Okay, well, we don't want to delve deeply into equivalence relations here, but so you just get the idea there, I hope. Now, some other things we want to prove here, this last page. Something I want you guys to recall here. Do you remember we showed this, that the determinant of a product of two square matrices of the same dimensions, right? That has to be the case for this to make sense. The determinant of the product is the product of the determinants. And therefore, we could actually turn this around and see that this is what? The determinant of the reversed product. So this is the formulation we're going to use. The determinant of PQ is the determinant of QP. Okay? P and Q have to be what? Square matrices of the same dimension for that to even make sense. Okay? So this is recall. Okay, if you don't recall that, go look it up. Okay, we're going to use that little factoid right now though. Proposition 1, if A is similar to B, or you could even say now, if A and B are similar, if you wanted to read it that way, that would be fine now, because it's symmetric, okay? But I'll just read it this way. If A is similar to B, then they have the same determinant. Okay? Let's see why. Well, if A is similar to B, that would imply that A is P inverse BP for some P. Okay? Let's take the determinant of A now. Well, the determinant of A would be the determinant of P inverse BP, right? Okay, just substituting our formulation there. Okay, now here's what I want to do. I didn't jump in here with parentheses just to shorten this here, but I'm going to think of it this way. I've got what? P inverse, and then I've got a single matrix. Think of it this way, a single matrix, BP. Okay, so I'm just thinking that as a single matrix, that product. Well, from above here, what we found is that that's actually the determinant of what? The product of those two matrices in reverse order. Okay, so that would be the determinant of BP times P inverse. Okay, the determinant of that product. But wait a minute. We have an associative property here, and I could go, what? B times PP inverse. But what's PP inverse? PP inverse is I, the multiplicative identity, so I've got the determinant of BI, but BI is B. So I've got determinant of B. Look at the first and the last. The determinant of A is the same as the determinant of B. What's this little open square mean? It means we're done. There, I'll fill it in. Finis. Okay, we got it. Okay, another little proposition here. If A is similar to B, then they have what? The same characteristic polynomials. Okay, let's go ahead and see why that's true. The characteristic polynomial of A in X, right? All right, we're using the variable X now instead of lambda, is the determinant of what? Xi minus A. Okay, so that's just definition here. Now, what's A again? Oh, A is going to be P inverse BP for some P, right? So I've got that substituted in there. So I've got the determinant of Xi minus P inverse BP, okay? Now I want you to notice here that I'm going to rewrite I here in the following way. This is actually what? P inverse Xi times P, okay? Now X is just a scalar, right? These other capital letters are matrices here. But I could move this scalar, obviously, any way I want. I could move it right out the product of these three, in which case I would have what? X times P inverse IP. But P inverse IP would be what? P inverse P, which is I. So I'd have Xi. Okay? Ooh, that's clearly the same thing. This is an awfully fancy way of writing what? X times I, but there it is. Okay? Notice that in the second product here, I also put B in parentheses for a little emphasis here because we're going to see what's happening here. Notice that I'm doing the same thing to both of these products here. I've got these products that are essentially doing the same thing. What am I doing? I'm multiplying on the left by P inverse and on the right by P in both products. I could actually write it this way. P inverse Xi minus B times P. Is that clear? Okay. All right, you would just use what? The distributive property. You don't have an associative property, remember, when you're multiplying matrices, but you've got a distributive property inside there. And you see that this P inverse would multiply on that, and it would multiply on that over on the left. On the right, you would multiply it by the P, and you'd be right back here with what we've got here. So these two are equal, okay, because they're the same thing in here. But wait a minute. Do you notice that what's inside the big parentheses here is actually similar to this, xi minus b. Yeah, it's similar to xi minus b, because I'm just going what? P inverse blah blah times p. So this is, whatever's inside this is similar to this. But that means they have the same determinant, doesn't it? Ooh, proposition 1 above. Yes, they have the same determinant. So that's the same as the what? This is equal to the determinant of xi minus b. But wait a minute, the determinant of xi minus b is known as what? The characteristic polynomial of the matrix B. Therefore, looking at the first and the last and ignoring everything in between, ultimately we've got what? The two characteristic polynomials are equal. Okay, QED, I got it. Okay, I filled it in. Last thing, if A and B are similar, then they have the same eigenvalues. Well, why would that be true? Well, this is obvious now from proposition 2. The eigenvalues of A are the zeros of the characteristic polynomial of A. The eigenvalues of B are the zeros of the characteristic polynomial of B. Those are the same polynomial we just showed above. So they have the same eigenvalues. Voila. Okay? All right. I hope that helps you along. We'll be talking about diagonalizing matrices and stuff very soon. Okay.